complex number. So complex numbers are actually something that you have learned before in Algebra 2 and again possibly in Algebra 3. Does anybody remember what a complex number is or looks like or anything?
They're generally in the form like a plus bi.
A plus bi, and that's what I have on my very first slide. That's called standard form for a complex number. Oh, Mrs. Baker, do you have all your
Oh, yeah.
little guys?
I put those away. They told us to keep them.
You followed directions. No, that's okay. Who's my green light on? No, my light's not even on. Okay, now let's get back to this. That's on my first slide, a plus bi. So the first time you learned about complex numbers, you started talking about that imaginary unit I. Now something to note is that not all complex numbers are imaginary. Complex numbers includes imaginary numbers and real numbers. So the real numbers, like the numbers we use every day, 1, 2, 3, are the numbers in complex form 1 plus 0i, 2 plus 0i, 3 plus 0i. They just have no imaginary part. So they're considered complex. The real numbers is a subset of the complex number set. And then, of course, you have things that do have an imaginary part, and then they become imaginary numbers, like 2 plus 3i, 4 plus I, 5 minus I. And then there is, within the imaginary set, there's a set called the pure imaginary numbers. They're numbers that are only imaginary and don't have a real part. So those are numbers like 5i, negative 11i. If you don't have a real part, we would call that pure imaginary. So just to refresh your memory, I might write down A is the real part and B is the imaginary part. Obviously, it's with the imaginary unit. It seems like some of us remember graphing complex numbers and some of us have no recollection of graphing complex numbers, so we'll just go over it really quickly. You can't graph a complex number on the real coordinate plane that we know with the x and the y axes because both the x and the y's are made up of real number units. So we have to have a new plane. We call it the complex plane. And in the complex plane, your horizontal axis is your real axis, and your vertical axis is your imaginary axis. And then you plot your complex number a plus bi. You move a left or right on the real part, or the real axis, and you move b up or down on the imaginary axis. Okay. Yes, sir?
Can you have functions on the complex plane?
You could have different things, yes, graphed on the complex plane. And the complex number set is the number set that creates really cool things like fractals, if you've ever studied any of those. But I will say this, in all of my years of schooling, I have never graphed anything more than just a complex number. So I wouldn't know very much about graphing functions, but I would assume yes, you could do more than just graph points. And then we want to talk about absolute value. So does anybody have a definition for absolute value just in terms of real numbers? What's the absolute value of a number mean?
The distance the number is away from zero.
Yeah. Okay. So in real numbers, we say the absolute value of the number is just its distance from zero. Since it's talking about a distance, we say the absolute value must always be positive because it wouldn't make sense for us to label a distance negative. You drive 2 miles to school and 2 miles from school, not negative 2 miles home. So you always say distance is positive. Now, in this picture, 0 would be represented by the origin. You could think about that as the complex number 0 plus 0i, or the ordered pair 0, 0. But you would go back to that origin. the intersection of the real and the imaginary axis. So I'm going to go ahead and plot that point right there and then draw the line that represents the absolute value. Okay. And I'm going to label it the absolute value of z. Z is just the common variable that goes along with complex number set. So tell me, how would we be able to find the absolute value of z? Could we do Pythagorean theorem? I think yes. I love that you saw that right away, Dylan. This would create a right triangle. We would know we went A units on the real axis, we went B units on the imaginary axis. So we now know that the absolute value of that complex number is the square root of a squared plus b squared. What else could you have used to find the absolute value besides the Pythagorean theorem? Oh, we are going to do sine and cosine to write the trig form. Okay. But I don't know that that would help us get its distance from 0. Oh, because then you want to solve for the side. Okay, so I could see that, yeah. Probably the answer that I'm looking for, think back to the ACT reviews we did. Distance formula. You're doing distance between 2 points. But I like the idea, Lily. I'll have to look at that later. See what that looks like. So on the next slide, I'm just going to give this complex number to you, 3 minus 4i, and say do those two things. Please plot it on a graph, and then calculate its absolute value, its distance from 0, if you would. So plot z equals 3 minus 4i, and find its absolute value. Okay, real quick, in your small groups, kind of share out. Do you have the same graph? Is it located in the same area? And then what did you get for absolute value? See if you agree or disagree.
Oh, that's a minus. You get 5 because they have
Okay, check up at the screen. Your point should be plotted somewhere in the 4th quadrant, 3 to the right and 4 down. And remember, when you're plotting a complex number, you're just plotting a point. Okay, so you don't need to draw the line back like we would with a vector. Okay. To find its absolute value, you would just do the square root of, it would be 3 squared plus, and then the b value is negative 4 squared. Don't include I with that, you're only doing the b squared. And so you come up with the square root of 25, which is 5. Now, note that if your absolute value does not come out to like a perfect square number that can be square rooted, then just simplify. Okay, reduce the radical, so the square root of 24 would be 2 squared root of 6. And do those same things we would normally do. Any questions with working with a complex number? Okay, so this form that we're working with is called rectangular form. So we called it standard form. Okay. And it's really in rectangular form as well. Calling it rectangular, what we mean by that is saying, like, for the values a and b, you move left and right, up and down. we want to change it so that we can now write complex numbers not just in this rectangular form, left, right, up, down, but we can write it in trig form. So a trig form would be in terms of an angle, okay, so the angle would tell you like the direction, and a distance would tell you, if you're thinking about vectors, a magnitude to move. Okay, so it would tell you how far out to go on that angle. I'm going to show a picture here, and I usually put the point in quadrant 1, but in this picture I just put it in quadrant 2. It could be in any quadrant. Okay, so it doesn't always, I always draw it in quadrant 1. I wanted you to do one where I'm drawing it in a different quadrant. Okay, so I've graphed a complex number, a plus bi, in its rectangular form. I went left a units, up b units. And to write it in trig form, we would like to see it, instead of a's and b's, which remember mean left, right, up, down, we want it in terms of r and theta. So your job is to think about how can we, knowing a and b, change to r and theta.
Always in the, what is it, arc theta? No.
What do we often do with this picture?
Draw a triangle.
We draw a triangle. So let's draw a triangle, right? Draw a right triangle in this case. Okay, so draw the right triangle. This time we got to go down to the x-axis on the left there. And by drawing that right triangle, thinking about a rectangular form, we now know two sides of that right triangle. We went left a units and up b units. Some people might be worried about this because theta is on the outside of the triangle instead of on the inside of the triangle, but you'd be using your knowledge from chapter 4, which is this reference angle, theta prime, for this triangle, has the same sine, cosine, and tangent values as the angle theta over here. Okay, so that we can put theta inside that triangle there. And tell me now, what equations can we write so that we can put A in terms of r and theta and B in terms of r and theta? What would be some trig equations we're allowed to say in this picture?
So sine of theta equals b over r, and then then just simplify it, or then.
I thought you were going to say the next one.
I was going to, and then I didn't want to like jump in.
Oh, I see. Saving some for the others. So we could set up two trig equations. Sine of theta is equal to a over r, b over r, and cosine of theta is equal to a over r. And then could you solve for a and b? Get a and b all by themselves? Yeah, and both equations just multiply by r. What are you going to say, Mason?
R is equal to the absolute value of AB.
Okay, let me write this down. Okay, so this is going to be helpful to us, right? We now know A in terms of r and theta and B in terms of r and theta. And you wanted to say r is equal to?
The absolute value.
Oh, the absolute value of the complex number A plus BI, right? What is the absolute value of A plus BI?
The distance from the origin.
Which is calculated as?
The square root of theta.
Yeah, so we know r is a squared plus b squared. Anything else you guys want to write on that one? Star? What do you mean?
Just add some.
Oh, just flare it out.
How about some great jobs for some positive reinforcement?
Way to go. That's my great job. I think the only other one, think about your trig equations. What's the other trig function? Tangent. Okay, so we could say that the tangent of theta is equal to B over A. Okay. But what's really going to be helpful to that is that theta is equal to the inverse tangent of B over A. And those two should look familiar from vectors, right? This is magnitude and this is direction angle. So those two come to us from the vectors. This should also look somewhat familiar to you from vectors. It's like the component form with the magnitude and the direction angle in it, like the magnitude of V times the cosine of theta, the magnitude of V times the sine of theta. Okay, so what we really want to do now, though, is after we found all these cool trig equations, way to go, nice job, awesome, okay, we want to put them into this rectangular form, do some substitutions so that we get it in trig form, in terms of r's and thetas. So what is A? R cosine theta plus B, which is R sine theta times I. That's trig form. It doesn't have the rectangular directions, left, right, up, down, A and B anymore. It has it in terms of an angle and in terms of a distance. Okay. Now, what do you notice is similar in both of these terms? They both have R. So most of the time a mathematician would write this out as R times cosine theta plus, and then for some reason we're going to move the I in front, I times sine theta. This one is fine, this very first one that we got. I would not take off if you wrote it like that. It's just most people will factor out the R, so they only have to write it once. And then, because mathematicians are often very lazy and don't want to write a whole lot, we have a new abbreviation that we'll use for all of that. And it looks like this. R kiss theta. Make a mental note to yourself. Kiss is not a real trig function. Okay, there is only sine, cosine, tangent, cosecant, secant, cotangent. Okay, so kiss is not a trig function. Kiss stands for cosine theta plus I times sine theta. It's just that you don't have to write all that stuff out if you don't want to. Isn't that nice?
Is it in like calculators?
No, it's not a thing. It's just an abbreviation. I don't think it's in your calculator. It's not a real function, right? It's just a way to shorten what you're writing.
It's not even a real number.
Now there are two vocab words that go along with this. They are modulus and argument. They're kind of like the vocab that we use for vectors, the magnitude and the direction angle. Okay? And then if you think back to trigonometry, it's the radius and the angle. Okay? So the modulus is R and the argument is theta. I use like R's and thetas, radius and angle, and argument and modulus. I kind of interchange all of them. But I want you to be aware of that in case you read something in a direction that says something about the modulus. And you know that represents R. Okay? Okay, so using all these wonderful things, I'm going to start a few more things right here. Nice, nice, nice. Okay, using all these wonderful things that we know about what A equals, what B equals, what R equals, what theta equals, we can go back and forth between trig form and rectangular form. Here's your first example. Right, 6 minus 6i in trig form. For me, number one key is what form is it in? A plus bi. I usually write that. That helps me. What form do I want it in? Trig form. R kiss theta. So that means I need R and I need theta. How can I get R? Oh, sure, I could find the angle first. How do I get the angle? Inverse tangent of b over a, which happens to be negative 6 over 6. That's the inverse tangent of negative 1. Oops. You could put this into your calculator, and your calculator will give you the answer negative 45. Remember, just like we do for vectors, I'd like that to be between 0 and 360. And you could also do this one without a calculator because that's a tangent on the unit circle. So think about what angles have tangents of negative 1. They're in quadrant 2 and quadrant 4. Which one do we want for 6 minus 6i? Quadrant 4. 6 to the right, 6 down would land me in quadrant 4. So I would want to say that the inverse tangent in quadrant 4 is the angle 315 degrees, or you could say 7 pi over 4. You can use radians or degrees. Either one is acceptable. Okay, so Lily said, find the angle. What else do we need? R. How do we find R? Distance. Same thing as absolute value, Mason said. Pythagorean theorem, Dylan said. Square root of a squared plus b squared. So the square root of 6 squared plus negative 6 squared. That's the square root of 72, which is 6 square root 2. You could also think about Ethan's argument from our ACT prep. That would be an isosceles right triangle, so I know the hypotenuse would be 6 square root 2. So I have r and I have theta. Just put them into trig form then. I'll say 6 square root 2 times kiss, and you pick if you want degrees or radians, 315. If you don't like kiss, you can write it in the long form. The long form would look like 6 square root 2 times the quantity, cosine 315 degrees plus I times sine 315 degrees.
If I use that, I'm gonna forget the actual.
If you use kiss. Yeah, so be careful, like kiss is, that's why I said kiss is not a thing, kiss is an abbreviation. So you have to know kiss is cosine plus I times sine. Okay, that's what that means. Are we okay with this?
Yes.
Okay, so then you should be able to go the other direction. What if I give you a complex number in trig form? Then can you please get me the complex number in rectangular form? So now I'm giving you the answer that we got last time. Put it in a plus bi. I'll give you a minute or so to come up with a plan and look back at your notes so far, see if you can come up with any ideas. Anybody have an idea to share about what we may do? Where could we start? Ethan.
Use the unit circle to find. Use the unit circle to find where it is and find an angle so that we can just start figuring out what the side lengths are going to be.
Okay. And then what are you going to do with the side lengths when you have them?
Well, what I did was I took 2 pi over 3, found it on the unit circle as 120 degrees.
Correct?
Then used the reference angle of 60 degrees, recognized it as the 30, 60, 90. And then from there I was able to use A as the hypotenuse, multiplied it by 1/2 to find my A, and multiply it by radical 3 to find my B.
Okay, like when I'm listening to what you're saying, I think you're doing an extra step that you don't need to do. Do you need to, from the unit circle, do anything with the reference angle of 60 degrees? No. when you go, like, that's the benefit of the unit circle, right? So if you're using the unit circle to jump right to 2 pi over 3, you can look at the coordinates for 2 pi over 3, which I would expect you all to still know, right? Okay, look at the coordinates for 2 pi over 3. They are negative 1/2 and square root 3 over 2. And that's giving you, remember from the unit circle, the cosine of 2 pi over 3 and the sine of 2 pi over 3. So, Ethan, what you're describing is more like going back even further and then working back up to that. But I'm going to say, since I know the unit circle, I know the sine and the cosine now. Okay? Not that your way is wrong. Okay, it's fine. You would have to be really careful because you're missing a negative sign. Because you're going left 1. Okay, so that's an idea, using the unit circle. Anybody else have any ideas then after we're kind of talking about that? Maddie?
I just put it back into the original, like, B equals R sine theta and A equals R cosine theta. And
Yeah. If you kind of flip back in your notes a little bit, we said these things about A and B, right? I starred them before we left that page. Gosh, I'm having a hard time changing my trig functions today. And so Maddie's saying she knows A is R times cosine theta. She knows B is R times sine theta. So let me just plug in my R and my theta, right? I know R is 8, and I know theta is 2 pi over 3. So she's going to do 8 times cosine 2 pi over 3. And this is where we could jump on to Ethan, his method. Using the unit circle, we know the cosine of 2 pi over 3 is negative 1/2. So we get negative 4 for A. And then we do 8 times sine of 2 pi over 3, which, again, going back to our unit circle, we know is square root 3 over 2. So that's giving me 4 square root 3. And then I can plug those back into A plus BI. So you could say your final answer would be something like negative 4 plus 4 square root 3i. Some of you might like to write that as negative 4 plus 4i square root 3. Just so that the I isn't hanging on back. Either one is fine. Sorry, I'm trying to get that square root better. Are we okay with that? Ethan, you see what I'm talking about with my negative there?
Yeah.
Okay, good. Okay, we have one other thing to talk about, and that is the product and quotient of complex numbers. There are formulas for this, so I'm going to go ahead and put those up and let you copy them down, then I'll say what they all mean. If you are curious about how these formulas came to be, I would say tonight when you're working on your homework, check in the textbook for the section where they start to talk about the product and the quotient of the complex numbers. And they actually write out the two complex numbers and then go ahead and distribute, multiply, simplify, and that's where this comes from. Just in interest of time, we're not going to do that today. But again, if you look at it tonight and then, pop in before after school or during one of our review days, ask me if you're curious about where the formulas come from. I think so. I'll have to check. I'm pretty certain that you need to know them. I think this is what I would say. Think about the patterns, because once you recognize the pattern between multiplying and dividing, it's really not so bad. Okay, so first thing I'll say is on this very first one, you're taking two complex numbers and multiplying them. Remember, z is just a representation for a complex number. So complex number number 1 and complex number number 2. In order to multiply those complex numbers, you're going to take the modulus of each complex number and multiply the modulus. And then you're going to do KISS, so cosine theta plus I times sine theta, for not just one theta, but both thetas added together, so the sum of the thetas. Okay, so if you're doing multiply, you multiply the modulus, you add the arguments. If you're doing division, then you do the opposite of those things. Divide the did I say add the arguments? Or add the modulus? Add the arguments, I said it right. Okay, if you're doing division, do the opposite of those things. Divide the modulus for each complex number, subtract the arguments. Okay, so they're really like the same thing, it's just in multiplication you use multiply and add, in division, divide and subtract. There is a limitation to division. Your second complex number cannot be 0 because you still can't divide by 0, not even in complex numbers. Not a thing.
Would that just be 0 plus 0i?
Yes. Okay, so here's an example. Find the product of 3 KISS 60 and 4 KISS 30. So I look back at my product and quotient formulas. I know that to multiply two complex numbers, I first have to find the modulus of each and multiply those together. So that would be 3 times 4. And then do KISS. And for the angle, add the angles, the sum of the angles. So that would be 60 plus 30. I'm showing my work here. You should simplify that. You'd get something like 12 KISS 90. If the book or the directions on the test say leave it in trigonometric form, you'd be done. That's in trig form. If the direction said get it in standard form, then you'd have to do that work that we did on the previous slide, finding A's and B's. Now, what's nice about changing into standard form, you can do it separately, kind of like what Maddie talked about. A was equal to R cosine theta, B was equal to R sine theta, and plug it in. Or you can just write this out. Like, what does KISS 90 mean? 12 times the cosine of 90 plus I times the sine of 90. And then evaluate those two trig functions. What's the cosine of 90? 0. And what's the sine of 90? 1. So that's really just 12 times 1i, or 12i.
Are we going to be allowed to use like the test this year?
Use what?
Yeah, KISS.
Yes, you can write KISS. Absolutely. I often use KISS, so like in our notes tomorrow when we extend our knowledge from today to do powers and roots of complex numbers, I'm going to be writing KISS a lot. You know, managers was like, yeah, that sounds really fun, powers and roots. I'm excited. I like that excitement, man. That was not happy. It was more like, are we okay with this? And I would just say, like, pay attention to what directions say. So, do you need to leave it in trig form? Do you need to get it out of trig form? Okay, and vice versa. Note that when you multiply complex numbers in their standard form, you often end up with like those I squareds, and then you have to change I squared to -1. Okay, so you can still multiply complex numbers in their rectangular form. We'll just finish real quickly. See if you could do this one on your own. Find the quotient of 12 KISS 70 Divided by 3 gives 25. And if you can get to the trig form, then see if you could change it into rectangular form. So it's a good practice just for that chance. Or convert. Four kids 45? That'd be 4 times the square root of 2 over 2 plus I times square root of 2 over 2. I'm doing cosine and sine of 45. And then distribute my 4, I'd get 2 square root 2 plus 2 square root 2I. You have a homework assignment. Do your homework, come with questions. Tomorrow we'll look at those powers and roots, and that will be the last of our notes for chapter 6. Don't forget today's Wednesday, so you're going to advisory.
This was. What was it?